Hi, welcome back to Signal and Systems. Today we'll talk about Lecture 4. The title of Lecture 4 is Fourier Series. You might not heard of Fourier Series before these lectures, so it will be very introductory lectures to Fourier Series here. So first we'll talk about introductions to it, and then we'll represent signals in sinusoidal functions, where it is very important in our Fourier Series. And then we talk about how we can compute Fourier series using the sinusoidal functions that we just represented. And then finally followed by properties of some of the Fourier series or frequency response. The module learning outcomes for these lectures will be on LO2, which is to illustrate the applications and uses of the Fourier series and Fourier transform in the analysis of signals and systems. So for today's lecture, it will be on Fourier series, and for the next lecture will be on Fourier transform. And so usually, how do we represent a signal? For example, for the second examples, let's say we don't have a clear signals, not something like 12 cosine of 12t, but we have some random signals, which is in the form of speech signals, which has multiple frequencies that we cannot really tell what frequency it has. So we need to have some tools to change these time domain signals into its frequency domain. So in terms of frequency domains, after you have changed time domain signal to frequency response, you have certain informations on different frequencies that these signals might have. And therefore, there are some particular applications that frequency response are actually quite useful, which you will see for examples at the back later. So before we go into the applications of using frequency response, let us look at how we can generate frequency response from any time domain signals. So this one will be the time domain signals, and how we can generate spikes of multiple different frequencies for our frequency response. So this person named Fourier has found one thing, that all signals, any time domain signals, can be represented by a constant. So this one is a constant with the summations of many cosine and sine signal. And this cosine and sine signal has different frequency. So look at the general formulas here. The frequency starts from cosine of omega t, then cosine of 2 omega t, then 3 omega t, all the way until infinitely many frequency. And similarly for sine here, sine of 2 omega t, 3 omega t, until the infinitely many frequency for the sine wave. So this Fourier has says that any signals can be represented by a simple constant plus summations of multiple sine and cosine wave. So let us look at a few examples in the next slide. So we have 4 examples in this slide. The first example is a square wave. So let's say we have a square wave as our signals, and then now we need to represent this square wave in terms of summations of multiple different sine and cosine wave. So if you look at the orange graph here, you can see that this is just a single sine wave. And if we add this sine wave into another sine wave with higher frequencies, we obtain the yellow graph, the yellow curve. And then if we add another even higher frequencies component to the graph, we obtain the green one. And so on, we get the blue one. And the more higher frequencies wave that we added in, it will reconstruct back this square wave more perfectly. So similarly, for the sawtooth wave, which has this particular waveform, can also be represented by multiple sine and cosine wave with different frequency, and triangular form as well, and also the semicircle forms. But one limitation that these representations work is that the waveform that you are going to decompose into sine and cosine wave must be a periodic wave. So this must be a periodic signal. Then only you can use this method. So this diagram shows the breakdowns of multiple different sine and cosine wave to generate our square wave over here. So the more you use, the more square the wave will looks like. And as you can see from here, if you travel back to higher and higher frequencies, the magnitudes of your sine and cosine wave actually getting smaller and smaller. So for visualization purpose, I have simulate a sine wave, or I simulate a bunch of sine wave added together to show you how close it is to becomes a square wave. So the first one, which is our original sine wave, that looks exactly like a sine wave in time domain. And in the second form, I add the original sine wave to 1/3 magnitude of a sine wave that is 3 times frequency of it. And you can see that this now has the ripples around the tops of the sine wave. And then I add even more sine wave into it. 1/5 of sine 5t, 1/7 of sine 7t, 1/9 of sine 9t. And it becomes more and more like a square wave itself. So the square wave should looks like this. So it becomes more and more like the square wave. And as I simulate it all the way until 99 sine 99t, you can kind of see that it is exactly a square wave now. So you can try it in MATLAB yourself. Just type out this equation. You just use a for loop to find out maybe to 1/999 of sine of 999t. And then you should be able to get a very clean square wave generated from your MATLAB. And indeed, this will be your lab. This will be part of the lab one that you are going to work on later. And so, by representing a signal into summations of multiple sine and cosine wave, or multiple periodic wave, we call it a Fourier series of the signal. And so these are some of the applications of Fourier series in engineering. And next, let us look at how we can represent a sinusoidal functions, because now every signal can be decomposed into infinitely many sinusoidal functions. So it is not really easy to write each and every sine functions out. So there's several way you can represent the sine functions into. We'll talk about it one by one in the next few slides. And the first one would be in the equation form. So in equation forms, we can write a cosine signal that has an amplitude of A0 followed by the frequencies of omega naught, and this frequency is in terms of radian per second, multiplied by the time t plus an offset, and this is called phase. And this phase is phase in radians. So if you have the frequency in terms of hertz, then you need to convert it using these formulas where omega equals to 2 pi f. So this is the general forms of writing out a general cosine wave. And for all sine wave, you can actually represent it in cosine wave as well, with just a phase change, a phase difference between them. And the second method will be plotting out the time domain graph, which is what we usually do. So for the same equations, if we plot it out in the time domains, you will have a cosine wave with the amplitudes of A0, and then with a phase difference of theta naught divided by the omega naught. And this length here will be representing the phase difference between them. The third one will be the frequency domain spectrums, and this is how you can represent signals in frequency domain. So in frequency domains, there are two main components. One is called the frequency, which is on the left graph here, and the other one is called the phase. So for the frequencies, we usually have a spike that is of the magnitude of, for example, in this case, magnitude of A1 with the frequency of omega 1. So this one is omega 1. And therefore, at frequency omega 1, we will see a spike that go up to A1. And this point is A1. And if we have summation of multiple cosine wave, we can actually adding on into these frequency domain spectrums. For example, we have omega 2. Let's say this is omega 2, 2 pi f2. And we have a magnitude of A2. And so there is a spike at magnitudes of A2 at this omega 2 frequency. And as for the phase difference between the phase difference of the cosine wave, we also write it at the same omega 1 frequency where we have a phase difference of theta 1. And at the same frequencies of omega 2, we have a phase difference of theta 2. So in these examples here, I was drawing a negative theta 2. That's why it is going towards the opposite direction. And therefore, please remember, frequency domain spectrums will definitely have a frequency graph and a phase graph, or we call this the magnitude graph. The magnitude graph and the phase graph. We have an examples on the same frequency domain spectrums, but before we go into examples, I wish to emphasize that due to the different textbook that we are using, some textbook returns the radian per second frequency as big omega, and some written as a small omega. So in our case, those two are the same. So sometimes you will see notes on big omega, and sometimes you will see notes on small omega. But just remember, they are both representing frequency of the signals in terms of radian per second. And it is always 2 pi f, where f is in terms of hertz. Alright, so let us look at this example. So in these examples, you are going to plot out the frequency spectrums of the curve of this graph, where you have three different components. First is the cosine of omega naught, and then second is a cosine of 2 omega naught, and third is a sine of 3 omega naught. You have actually three different frequencies here. And as you've seen earlier, all our magnitude must be positive. So this negative b, we have to change it to a positive b, and by doing a frequency phase shift of 90 degree. And then for all sine wave, it is better that we change it to cosine wave. And to change to cosine wave is just a phase shift of negative pi over 2. And therefore, we can represent this particular graph as a cosine omega t plus b cosine 2 omega t plus pi, and plus c cosine of 3 omega t minus pi over 2. And therefore, we have our three spike, one at omega naught, one at 2 omega naught, and the third one on 3 omega naught, and each of their magnitude equals to a, b, and c respectively. As for the phase change, for the first a cosine t, there is zero phase change, so there's nothing here. It's just a zero, it's just a dot over the zero axis. And for the second 2 omega naught, we have a phase shift of pi, so this one corresponds to phase shift of pi. And for the third one, we have phase shift of minus pi over 2, so you draw up to the negative pi over 2 axis. So this is how you can draw the frequency domain spectrums of a given time domain signal. And next up is the phasor forms. So we are allowed to draw any cosine wave with any amplitude, frequency, and phase difference into these phasors forms. So in order to do that, we first need to change all the cosine wave into amplitudes and angles with frequencies times the time domain, the time signals, plus the phase. And therefore, look at these examples. So for cosine omega t is just simply v angle of omega t, and cosine 2 omega t plus pi over 6 is just simply v angles of 2 omega t plus pi over 6, and so on. And then when we draw it on the phasor form, we always start from the x-axis. So from the x-axis, we draw our first cosine wave, which is to have a separations of omega t angles, and that's all. And then this line will have the length of v. And then from the same axis, which is starting from here again, we will draw the second phase, which is at this 2 omega t plus pi over 6. So we go all the way 2 omega t, should be roughly around here, and plus pi over 6. And then that is where we can draw a second line. And so we can also follow the same methods to draw our third line. And if you have more components, you can actually draw even more lines for that. And the next one is a static phasor form. So this one is very similar, is actually a subset from our previous phasor form, but now the static here means that each of the frequency components of our graph, the main frequency component of our graph, they are the same. So if we have the frequency component of the graph are all the same, for example, this angle of omega t plus pi over 6, angle of omega t plus pi over 3, we can actually ignore the omega t when we plot it out in the phasor form. So for the first one, it's just v at angle 0. So it's just all the way a straight line to v. And the second one is just the angle of pi over 6. So we have pi over 6 and we draw up to angle v over 2. And the third one, pi over 3, draw up to angle v over 3. And so this is the static phasor form, where the angles we can ignore the omega's frequency. And finally, we have the complex exponential form. And this form is one of the most used form and one of the most important form as well among all the 6 forms that we have shown earlier. And this form need to use principles of Euler's formula. So if you still remember Euler's formula, it says that e power to j theta is actually equals to cosine of theta minus j sine of theta. And if you look at Euler's formulas, if you write it when the theta is negative, so e power to negative j sine j theta. In this case, it will become cosine of theta plus j sine of theta. So the sign here actually changed. And what if you add them both together? So e power to j theta plus e power of negative j theta, I write it here, plus e power to negative j theta will be equals to 2 cosine theta. So look here, your j sine theta will be cancelled off because there's a minus sign here and there's a positive sign here. And you can also carry the 2 to the other side to become e j theta plus e minus j theta divided by 2, and it will be equals to theta. So using these formulations, any cosine theta can be represented as exponential signals. So therefore you look at this cosine omega t plus theta, the whole lump of things here, you can write it as 1 over 2, which is the over 2 here, same here, e power to j of the whole thing plus e power to negative j of the other things. And therefore, once you represent your signals into different exponential signals, you can now draw the peak easily. So you look at this frequency magnitudes, or sometimes you call it the magnitude graph, and this is the frequency axis. At this omega t, we have a magnitude of v divided by 2. That is why at omega we have a magnitude of v divided by 2. And now look at this one, or we look at the blue colors here. At negative omega, we also have a v naught over 2. So at negative omega, we have a v naught over 2 as well. If you look at how we are going to draw phase, so let's say this is the phase plot, and again, because we have omega and negative omega, so we have one omega and one negative omega here. And you look at this one, during omega, you have a positive theta. So this one will be positive up to theta. And during negative omega, you have a negative theta. So at this point, the peak actually going downwards to negative theta. So this is your phase plot. So complex exponential forms, you have both magnitude and phase plot. And usually, not usually, but always, all the time, your magnitude will be just a reflection on the zero axis. If you look at it carefully, every time you have a peak on the right at certain frequencies, then definitely you have a peak on the left at that particular same frequency. As for phase, it will be reflected twice. So every time you have a positive value at that positive frequency, then you will have a negative value at that negative frequency because of the properties of our Euler's formulation. Alright, so next let us look at how we can compute Fourier series of any signals. So because certain signals, they are quite difficult to find out the frequency components. For example, if I give you a square wave signals, you can't really decompose it into cosine of certain frequency plus cosine of other frequency. So there are certain mathematical formulations here that can enable you to compute it mathematically to find out what is the frequency components of any periodic wave. First is the complex exponential Fourier series. There's only two formulas that you need to work on, and you don't even need to memorize this formula because they will be given as in the formula sheets during your exams or tests. So in these two formulas, it says that any signals xt can be represented as summations of a constant ck multiplied by impulses. So if you still remember, earlier on when we draw this out, this is actually impulse at different frequency k omega naught. So in order to find out the expressions of this xt, the only things that we need to find out is a ck, and ck is given over here. So what you need to do is that whenever you were given a functions xt or signal or system xt, you just need to put in the signals or systems into these equations and then do the integrations over a time period t0. So this is over a time period, and then divide it by the t0 itself, and therefore you should be able to find out what ck is. And then this ck, for k, it corresponds to 0 up to infinity, so you get negative infinity up to infinity, so you get c0, c1 all the way to c infinity, or you get c negative 1 all the way to c negative infinity. But in most of the case that you work later on, you notice that many of these terms are actually 0. So for examples, all these are 0 and left with c0, just an example. So later on when you work on examples, then you will roughly get the idea of how to generate c0, and then finally you need to bring this c0 in to your final equations here. And one thing note to remember is that you should always convert between them. This is the frequency and this is the period of the period of your signals. So the frequency is in terms of radian per second, and this period is in terms of second. So the relationships between them, omega is equals to 2 pi over t. Now let us look at example 1. In example 1, you need to represent a very simple signals into Fourier series representations. This signals itself is just xt equals to cosine of omega t. And for this particular signals, you want to represent it in this form where it is a summation of a constant multiplied by impulses, or e power to j omega t with different k. So for this case, you don't even need to apply the formula to find out what ck is. What you need to do is that you just use the Euler formalism, where you can make cosine of omega t into just e power to j omega t plus e power to negative j omega t divided by 2. And this itself is already a Fourier series representations, because this is the c naught, this is the ck, and this is the impulse of that particular k, and this is the other ck, and this is the impulse of the other particular k. So in this case, there's only two k values, where k equals to 1 and k equals to negative 1. You can also just use the formulas to find out what ck is. At the end, you should arrive with exactly the same answer. But this examples is the most straightforward examples where you don't really need to apply any formulas. Just use Euler formalism and you'll be able to find out the answer. The second method for you to find out the Fourier series of any signals is to use a trigonometric Fourier series formula. So this formula works exactly the same like the complex exponentials formula, except that there are more items that you need to find over here. So for any questions, you are free to use either the Fourier series, the trigonometric Fourier series, or complex exponential Fourier series. So I'll just explain how this formula works. So for any signals, it can be represented as a constant plus a summation of cosine and sine wave with different frequency. So the frequency goes from omega naught to 1 omega naught, 2 omega naught, 3 omega naught, all the way to infinity omega naught. There is no negative number here, so k only start from 1. And then to find out what a naught, ak, and bk are, you just need to apply individual formula over here. This is a naught formula, this is ak formula, and this is bk formula. So sometimes, although this formula looks a little bit much longer than the previous complex exponentials formula, but one thing good about this is that it doesn't have the terms of e power to j k omega t, because these terms will make your integration difficult to do. So for this case, if you use the trigonometric Fourier series, it doesn't have this term. So it only has cosine and sine term. For all the very complicated integrations, complex integrations, I will be providing you a formula sheet with a lot of integrating spreadsheet that you can use it during your exams. So it'll be attached on your final exam as well. You can check it on your times. It should be uploaded by now. Like I said earlier, the trigonometric Fourier series computation and the exponential Fourier series computations, they are explaining the same thing. They are representing the signal in exactly the same way. Just that one is written in cosine and sine, and the other one written in e power of j omega. And then you can actually change them easily using the Euler formula. So if you remember, for the trigonometric Fourier series, you have a naught, ak, and bk. But for the exponential Fourier series, you only have ck. So the relationship between ak, bk, and a naught are represented here. They can be just substitute, and then you get the representations in another form. That's all. So in another way, you can formulate ck or c minus k using this formula, or you can find out ak or bk using ck as well. Alright, now let us look at the second examples. For these examples, you are given signals that has two different values. It's either 1 or 0. So these signals, if you plot it out, I will suggest all of you to plot the signals out whenever you will ask this kind of questions, so that you get a clearer idea on how you can do integration on this. So for these signals, whenever it's below 0 and up to negative 1, it's all 0. So I'll just draw a darker line here. And when it's above 0 and up to 1, it becomes a 1. So this is essentially your signals. And these signals, of course, like I said earlier, Fourier series must be done on periodic signals. So this signals is actually periodic. So it will keep going one by one. So this will be 2, this will be 3. And the negative sign is the same. So it's just like your sine wave signals. It is periodic. So for these questions, you are free to use either exponential way to do it, or you want to use the trigonometry way to do it, also okay. So in the solutions that I will provide in the next slide, I'll be using the trigonometry methods. So all the formulas are written here already. This formula again will be provided during exam. You don't have to memorize it. I don't expect anyone to memorize any of them. But please remember, omega is equals to 2 pi over t. And now our job is to find out what is A naught, what is AK, and what is BK. Alright, now let us look at the solutions for the problems I shown earlier. If you still remember the graph, let us draw it out over here. You have your x-axis, and this graph initially was 0, from negative 1 to 0, and it will rise up to 1, from 0 to 1. So first thing, you need to find out the periods. As I said earlier, this graph should be periodic. So these are the remaining of the graph that we didn't see. But to find out the period, it's very simple. You just find out the minimum and the maximum before it repeats. So periods is equals to 2. So our T naught is equals to 2. And then once you find out the periods, you can find out what is our omega naught. Our omega naught will be equals to 2 pi over T, when in this case it's just pi. Alright, the next thing, we need to find out A naught by applying this formula, and T naught will be 2, as I said earlier. And when you apply these formulas, let's look at the solution. You need to integrate your signal xt from any period of time, as long as it spans one period. So it's either you want to integrate it from 0 to 2 or from negative 1 to 1. Both are fine. You'll get the same answer on both things. So let us integrate it from negative 1 to 1. So in order to integrate from negative 1 to 1, you'll notice that this graph actually split into two different portions. The first portion is everything 0. The second portion, everything 1. So we also split the integration into two portions, everything 0 and everything 1, where the first portion span from negative 1 to 0, and second portion span from 0 to 1. And after you do the integration, these are very simple integrations, you arrive with the final answer as 1. Next, the more critical one, which is to find out AK and BK. So let us look at AK. Similar to A naught, you just apply the formula T naught equals to 2, therefore you put it over here, and you put back xt into it, and you need to integrate it multiplied by cosine of k omega t. But earlier we have said that omega is the pi, so it becomes a cosine of k pi t instead of cosine of k omega t. And again, like the previous case, we split into two different integration. One integration xt is 0, second integration xt equals to 1. So there is actually a 1 here, just that 1 multiplied by cosine, it becomes just a cosine. And now 0 again is nothing. And to integrate the cosine k pi t, you arrive at the answer sine k pi t. And then you need to substitute the limits from 0 to 1 into your answer, and finally you actually obtain 0 as your answer. So you can just try it. You substitute it 1 and 0 into these equations, and you finally obtain it as 0. And then the next step is the BK. So BK, similar to AK, just change the sign into cosine. And then again, similarly, you just integrate them into two different portions, and you arrive with this final answer. Substitute 1 and 0 into your t, and then you'll find out this is your final answer for BK. And there is one more step that you need to do. You need to find out what is the final xt by applying all this formula into it. So you just rewrite the whole thing. A naught is 1, so this one becomes 1 over 2. There's no ak at all because ak everything will be 0, and bk is this expression over here, and you just need to copy it down. The reason I change the sign is because this bk has a negative sign over here, so I just change to negative cos and plus 1, and that is your final answer. And this one will span from 1 to infinity. Alright, so you have already learned how to compute the Fourier series of given any signal or any systems. So next is how do we use it? So if you remember in the last chapters, when you learn about convolutions, if you have a signal in time domain that passes through a system, if a system is given to you the impulse response in time domain, your final answers, the output, will be just the input convolute with the systems. So in frequency domains, when you have already convert the signals and the systems into frequency impulses, and according to the derivations over here, which you can go through it slowly, it says that in frequency domains, the outputs of the signals, let's say y omega, is equals to the input of the signal multiplied by the impulse response of the signal, of the systems. So instead of doing convolutions now we are only need to do multiplications. Once you find out all the Fourier series in terms of frequency domains of your signal and systems. So that is the applications of frequency domain analysis, not just Fourier series, but later on you'll learn about Fourier transform, Z transform, and also Laplace transform. All these, the same properties will hold. Alright, this slide is similar to what I said earlier, except that now instead of using just an impulse signals, we are using a generalized signals, which is in terms of in the Fourier series representations. And you'll notice that the output will be the multiplications of the systems and the input. So it becomes a multiplication. So given these special properties of frequency response or convolutions in time domains is equals to multiplications in frequency domains, what are the things that we can do easily using these properties? So first thing is the filtering. So if you look at filtering, for example, you listen to certain speech signals, and this is your speech signals, which is very random in time domain. This is time domain speech signal, and you represent it in Fourier series. Either you use your Fourier series transformations using trigonometry or complex exponentials, you arrive with the frequency domain graph. So this one is in terms of frequency domain. You get several spike. For example, this is spike 1, this is spike 2, this is spike 3, this is spike 4. So each of these spike in terms of speech signals corresponds to actually your frequencies of your tones. So now, let's say the frequency of your tones is only at these several instances. And these high pitch frequencies, denoted in the blue color circles here, are actually somebody shouting at the background, and you didn't want this sound to appear in your speech signals. So what we can do is, I will show you in the next slide. So this is what we can do. Your speech signals, after you convert it to a Fourier series or Fourier transform that you learn later, you will obtain frequency signals where you get a few spike of your frequency. And then this frequency signal will pass through a system where the system's impulse response is actually a block, meaning that it is amplitude of 1 at frequency starting from 0 to certain frequency. So let me say this is FC, the cutoff frequency. So this block later on you will learn that this is called a low pass filter. This filter has an amplitude of 1 when it's low frequency from 0 to Fc, and beyond Fc is amplitude of 0. So when you have the signals that pass through such a systems, you can imagine that the signal that pass through the systems is the multiplicative. So these two signals and system will multiply together to obtain the output. So in the end, your output will be all the low frequency signals that is in front here, denoted by the blue color pointer. These are the low frequency signals. Let's say Fc is here. Anything before Fc is multiplied by 1. Anything above Fc is multiplied by 0. And therefore, anything above Fc is over here. So this is Fc. And your signals now becomes a clear signal where you only have your voice. Initially, there was a shouting on the background noise, but now this has disappeared because you have passed through a low pass filter. So I'll talk more about the low pass filter in the next slide. And this is the mathematic representations of a low pass filter. For low pass filters, first you need to select a cutoff frequency, omega c over here. Everything on the left side of the axis will just be the reflections on the right side, as I said earlier in the lecture. So we're only interested from 0 to omega c. Wherever between this one is 1, wherever after this is 0. So this one is a low pass filter, meaning that any signals that has frequency lower than omega c will pass through, and any signals that has frequency higher than omega c will not pass through. Therefore, it's a low pass filter. And similarly, we can design different type of filters. For example, this one is a high pass filter. A high pass filter also has an omega c, the cutoff frequency. Anything above omega c will pass through. This one is pass through. Anything below omega c will not pass through because it's multiplied by 0. So therefore, this is a high pass filter. And next, we can combine a high pass filter and a low pass filter to find a band pass filter. A band pass filter will pass any frequencies that is between two cutoff frequency, omega 1 and omega 2 in this case. So any signals that has these frequencies will remain, will pass through. Below this frequency, it will ignore. Above this frequency, it will also ignore. Similarly, band stop filter. Band stop filter is the opposite of band pass. Any signals that is between this band will not pass through, so it stops. So therefore, it's called a band stop signals. And now let us look at one example. You have a signal. Your signal has three components: a constant 1, a cosine wave with 2t, and a cosine wave with 4t. And now this signal has passed through a filter, and we have three different types of filters shown over here: low pass filter, band pass filter, and high pass filter. So now the question is, what is the output of the systems when you have these signals that pass through three different filters? So let us look at A first. A is a low pass filter, meaning any signals below 1 radian per second will pass through. Any signals above 1 radian per second will not pass through. So we look at our xt. Is there any signal that is below 1 radian per second? Yes, only the constant. This is below 1 radian per second. The constant is 0 frequency. Cosine of 2t is above 2, above 1 because it's 2t. Cosine of 4t is again above 1 because it's 4t. So now your output become 1. You have essentially cut off two of these terms. Your output will just be just a single 1 without any other frequency. Now let us look at case number B, where you have band stop filter, a band pass filter. So only things that is between 1 and 3 radian per second will pass through. So in this case, your output only is 2 cosine of 2t because only this one is between them. And similarly for case C, you only have things that above 3 radian per second will pass through, so your outputs will be 2 cosine of 4t only. No other signals can pass through. So this is one example of using a low pass filter. So initially, if you have a picture that's taken with very high ISO, in high ISO you notice a lot of dust, you call it dust, that is appearing on your photos. By doing a low pass filters, you are essentially cancel off all the high frequency noise that exists in your pictures in this case. So all these dust are considered as high frequency noise because it shows a lot of contrast between the two different pixels. And therefore, on the picture on the right is the image after you apply the low pass filter. And this is also how some of your phone doing the face beauty apps for you. As for high pass filter, it does the opposite things. It keeps all the high frequency data. So in this case, if you have a very clean original image and you apply high pass filter on your image, what it left is all the contrast between the two pixels. So for example, if you look at the shoulders here, at this particular line, on the bottom of this line is black colors, on the top of this line is white color. So at this line, exactly at this line, is of very high frequency because it changes from a very high value of 255 into a low value of 0 in terms of the colors of the image. And therefore, if you apply high pass filters into an image, into a clean image, you actually obtain the line tracking or the line tracing algorithms. So this is the outcomes on the right side. You will get the outline of that person when you apply a high pass filter. So this is just similar examples by using different pictures. Usually nobody will really use band pass filters because it kind of filters off all the high frequency noise, at the same time filter off all the low frequency as well, so it left kind of like outline plus a little bit of smoothing effect, but nobody really use it. So most likely people will use high pass filter or low pass filter in processing images. And finally, let us look at the properties of frequency response. So the properties of the Fourier series, odd and even signal. So if you look at your Fourier series, the formulations of Fourier series, I should write it over here. The total formulation is xt equals to a naught over 2 plus summation. I will not write what summation is it. Ak, this is the cosine of certain omega t, and then plus summation of bk sine of certain omega t. If you look at these signals, and you can imagine if your signals is an odd signal. Odd signals, for example, like your sine wave is an odd signal because the negative side is the reflections of it. The positive and negative are totally opposites. And in this sine wave, this is a sine wave, you can imagine if you put it in terms of frequencies response or in terms of Fourier series, you only have the sine term left. You don't have any other terms left. So therefore, when your signals is odd, for example, sine signal or any other odd signals, your A will all be 0. You left only with the sine term. So this is one property that you can apply. You can simplify your calculation. You don't need to calculate so many things. You don't need to find out what is AK, because no matter what you find, finally your AK will be 0. So this one will you can apply these properties on one of the examples we shown earlier, where after calculation you actually get AK equals to 0, if you still remember that question. And if you have an even signals, so even signals, for example a cosine signal that start from 1 and go down, it has an even property because anything on negative side and positive side is just a reflections on the axis, and these signals will have all your B terms to be 0, and therefore you left only A terms. A terms has cosine terms and has a constant term. So don't forget, you still need to have constant terms in even signal. The next property is the Parseval relations. It says that the average powers of a periodic signal is equals to the sum of magnitudes of the complex Fourier coefficients. So that's all for the Parseval relations. Alright, and that's all our lectures for today. You have learned about Fourier series computations, how you can convert time domain signals into train of impulses, or time domain signals into summations of cosine and sine wave. These two, they are actually the same. You can convert them using the Euler formula. And then you learn about different properties of frequency response, where you also learn on low pass filters, high pass filters, band pass filter, and band stop filter. And then you learn a little bit on the properties of the frequency response, such as the odd and even signals where you have only A terms or B terms, and then finally the Parseval relations. Alright, this is what you are going to learn in next week lectures, which is Fourier transform. Just a head up for you on Fourier transform. In this week, you learn to transform a signals, any signals, with Fourier series to find out in frequency domains. But this one only works when you have periodics, when you have a periodic signal. What if your signal is not periodic? Then, if your signal is not periodic, we still be able to get the frequency response of the signals, but this time we will be doing Fourier transform instead of doing Fourier series. They are very similar, and you will learn about it next week. See you next week.